Okay, I'm in the cafeteria, so if you hear some clanking in the background, it's just the kitchen workers preparing to serve food later today. All right, first off, this little section of notes, I've already uploaded this to It's Learning. It can be found under the PowerPoint section, Verifying Trig IDs folder, and this is Trig ID Notes, capital B. This worksheet was scanned in. Okay. So quickly to remind you guys, verifying trig IDs, it's basically a proof to show an equation is true. As a procedure, we are given an equation with two sides of the equation, and they will look different in the beginning, and your key is to get the left side to exactly equal the right side. Okay, so you only get to work one side at a time. You don't get to add something or subtract something to both sides of the equation. Very soon we'll be solving trigonometry equations, and you will get to do stuff then, but for right now, only work one side at a time. It's a series of substitutions and simplifications that's going to make one side of the equation equal the other, and then the reason that we don't get to add something or subtract something from both sides is because every single step along the way, each step is equal to the original statements. These are a few hints to keep in mind as you progress through. Start with the more complicated side. Express things in terms of sine and cosine. That is a good strategy. When you see the number 1 or a trig function being squared, think of the Pythagorean IDs. When you are combining multiple terms, if there are fractions, remember to use a common denominator, and remember conjugates for denominators, and I'll give an example where that will come into play. And this is just a reminder of the 11 trig IDs in no particular order. You will be given these IDs on a test or quiz. All right, now to get into lovely examples. All right, this is my first example, and I'm going to do each underlining in red so that you can see the substitutions I'm doing here. So I notice a sine squared plus cosine squared. One of my Pythagorean IDs. Maybe I can, yeah, I think I can do it like this. So we can have all the IDs here at the same time. One of my Pythagorean IDs, this guy right here, says that I can have sine squared plus cosine squared theta is really just equal to 1. So what I have underlined here in red, I'm going to replace in my next line with just plain old 1. Okay, now what I'm about to do, you guys don't actually have to show me these steps. You can just jump straight from here to the final step right here. But technically speaking, this is 1 over cotangent theta as a quantity being squared that we can then use 1 over cotangent is really tangent. And that, of course, is tangent squared theta. So this little steps here in green is just to show you that you don't actually have to worry about that squared. You can kind of, in your mind's eye, factor it out, do the trig substitution, factor it back in. The squared, that is. Anyways, that brings us to tangent squared theta equals tangent squared theta. And that is our goal, to get the left side to equal the right side. The only thing that I've done in this particular example is make a substitution here. Sine squared theta plus cosine squared is really 1. And then make the substitution 1 over cotangent is really equal to tangent. Pause the video if you need to look at that any further. Next example. Here, both sides of the equation look equally complicated. Oh, yes, let me remind you on that last one. You want to start on the more complicated side. It's easier to, if you imagine these like a little tree where we have all these little branches, it's easier to start with something really complicated and make your way back to the trunk than it is to start at the trunk, the easy thing, and find exactly the right path to get to the complicated thing. So you definitely want to start with the complicated side of trig ID. Anyways, both sides here look about equally complicated. I will start on the left. Now, remember one of the hints about the conjugate? In my denominator here, I have a 1 plus cosine, so maybe I want to multiply the numerator and the denominator of this fraction with the conjugate of the denominator. And another hint too, if you're not changing one side, you don't have to recopy it every step along the way. You can just leave the equal sign in blank. Okay, so let me finish this guy off. We're going to distribute in the numerator. And in the denominator, because we use a special factoring result, we have a special factoring result. This is the difference of perfect squares. So a 1 plus cosine times a 1 minus cosine is 1 minus cosine squared. And you can FOIL that out if you don't believe me. Okay. Next, this 1 right here, we can think of that as really sine cosine squared, sine squared, cosine squared. So the numerator stays the same. But in the denominator, instead of this 1, I'm going to substitute in sine squared theta plus cosine squared theta. And that's really convenient because positive cosine squared theta and negative cosine squared theta cancel out. So cleaning this up a little bit, I have, you know what, I think I may have gone in the wrong direction here. Let me do this in 2 steps. So just recopying, I have sine theta minus sine theta cosine theta all over sine squared theta. So sometimes you don't always go down the most efficient path. I wish I didn't distribute the sign in this last step. I wish I just left it sine theta times 1 minus cosine, and I'm actually going to go ahead and do that now, and you'll see why. We don't always go the most efficient path, but that's okay. We can back up and change things if we need to. Because a sign now will cancel here with 1 in the denominator. And I have 1 minus cosine theta over sine theta equals, sweet, look what I'm trying to get to. It was that the whole time. Verified. Okay, last example for this particular video. We're getting close to 10 minutes, so I want to keep this about 10 minutes, give or take a tiny little bit. Okay, in this example here, the right-hand side definitely appears to be the more complicated side as far as I'm concerned. I have tangent cubed theta as part of both of these terms. So I'm going to go ahead and factor tangent cubed theta out of both terms, and I'm left with a secant squared theta minus 1. But I see the secant squared theta and a 1 as part of the same expression, so I want to be thinking of my Pythagorean IDs, and in particular this one here looks pretty useful. It's got a secant squared theta and a 1. So maybe instead of secant squared theta, I can substitute 1 plus tangent squared theta. And that's really convenient because plus 1 and minus 1 are 0. And I'm effectively now looking at tangent cubed theta times tangent squared theta. And tangent cubed times tangent squared is tangent to the 5th theta, which was what I was trying to prove the whole time. Verified. Feel free to pause or rewind or watch any parts of this video over again. And we'll keep it under 12.